well, let's now look at what happens when we add the three windings together. So the MMF distribution for three-phase windings. So this is actually particularly useful for my students working with me because of the because if you come up with a new machine, then it might look good, and then you make a winding, and then you try to simulate it, and it has all this oscillating torque, so the reason for that often could be due to the winding interacting with the rotor fields to create additional harmonics that cause torque ripple. And so understanding the winding and what harmonics are present fundamentally is really useful if you're designing machines. So we looked at the particular phase winding, so now let's see what happens when we add up the three phases. So we talked about this at the beginning of this section on windings, but we didn't, I kind of did it with the sines, just assuming pure sine waves. So now let's look at this in a little bit more detail when we account for the harmonics and see what happens, because it actually turns out that some of them will disappear and that others will be rotating in opposite directions. So you'd be actually, some of the harmonics could be creating a braking torque. So we can see what's going on now, because we have a good picture of the winding. So the MMF is the winding function times the current. So we have so we can write out, like here, we can now write this out in a more general way. So we have summation n equals 1 to infinity, and n is odd. And all of this, n is odd. All of this analysis here. I'll try to make sure I write that. So we have and here we have P for pole pairs, not pole pairs. Here we have P for poles, so we divide by 2 will give us pole pairs. So that's why there's a 2 there. So I'll call this equation 1. And so this part here is the winding function. So then we have there's a little bit of playing around to get this. So then we have B. So the phase B is there okay? So phase B is n over pi. So this is a little bit mathematically long, but I think it's pretty useful. because it really, what this will show is really what harmonics are produced in a machine naturally from a three-phase winding. And so with the C phase is also phase shifted by 120 degrees. It's good that it's not 6-phase, otherwise it would be a little bit more time consuming. Okay, so this is equation 3. So now, the sine terms in 2 and 3, they can be changed using a trig identity. So sine terms in 2 and 3 can be written as, so we can note that we have sine A plus or minus B is equal to sine B times cosine, sine A times cosine B plus minus cosine A times sine B. Okay, so with that identity, we can then see that sine n p theta over 2 plus minus 2 pi over 3 is equal to sine n p theta over 2 times cosine 2 pi n over 3 plus minus cosine np theta over 2 times sine 2 pi n over 3. So that's equation 4. Okay. If we look at these phase A and phase B and phase C, we can see that both of these have the sine n p theta over 2. The only difference is the second term where it's plus and minus. So if we look at the identity here, again, the only difference is going to be the plus minus term. So with that in mind, then the first term here is going to be exactly the same for B and C. So we can then collect up some of these terms. So in order to look at the fields doing, we have to add up these 3 MMFs. So we have that the total MMF as a function of time and space, so this is spatial and temporal, is going to be the summation of all 3. So we have 4n pi, n equals 1, n is odd. Now I'm going to take out, so here we have kn sine np theta over 2. I'm going to take that and put it at the beginning for all of them. So we have kn sine np theta over 2. That's present for on all 3. And then that's going to be multiplied by the IA current plus, so the B and C, they both have this cosine term here. So we're going to have plus cosine 2 pi n over 3 times IB plus IC, like that. Okay, plus the second term, Kn. So we've got the second term. So the second term, there is no second term for A. A is nice and pure. The B and C are the nasty ones. They have this plus minus part here. So the the only difference is one is plus and one is minus, and the B is minus, right? So we're going to get a minus IB current associated with the current. So we have Kn cosine np theta over 2 times sine 2 pi n over 3, and that's multiplied by IC minus IB. Just managed to fit it. Equation 5. So we have the currents IA and IB and IC. So we got to this point. So what I was trying to get to was a equation that looks at what are the important harmonic terms within the air gap field for a rotary machine. So now we can keep going and simplify down, see where this takes us. So if we assume that there is no neutral current path, which is pretty reasonable. So if the machine has no neutral current path, then we can say that IA plus IB plus IC has to equal 0. All right, or IB plus IC equals minus IA. Okay, so then with this we can replace the first term with minus IA. Okay, so doing that. So this is 6. So 6 into 5. 6 into 5. We get out another long equation. And remember that because of being odd function, we only have odd harmonics. So n can only be odd. So this becomes the first term. So we've taken out the IA, and then we've got a minus now here due to substitution of 6. Then the second term is currently unchanged. Okay. Now we can, if you look here, when n is 3, the third harmonic, this term goes away. And here, when n is 3, this term goes away. So there is no third harmonic. That's pretty interesting, right? Note, for n equals 3, the MMF is 0. No third harmonic if no neutral. Now assume that the currents, so this is IA as a function of time. Assume now that the currents are implied that are phase shifted by 120. So assume that currents are balanced such that we have current A, IA, that's equation, I'm going to call that equation 8, this is equation 7, and then we have IB, and then we have IC. Okay, so we can then substitute these into 7. Before we do that, note that so we have IC minus IB. So then if we look here, we have IC minus IB. Right? What's that going to be equal to? That's going to be equal to the magnitude of the current sine omega ET plus 2 pi over 3 minus sine omega e over t minus 2 pi over 3. If we use a trig identity, this can be reduced down to 2 times Im cosine omega et times sine 2 pi over 3. You can check that. So with this identity here, we can then substitute that back into 7 here. Now sine 2 pi over 3 is equal to square root 3 over 2. So this simplifies down to Im square root of 3 cosine omega et, which is quite nice. Okay, so now now substituting that in, what do we get? So we're substituting this current back into here and playing around with it a bit more. So we get MMF is equal to, actually I'm going to just keep using this. So we're going to have this here, this now is a 1 here, that's a minus, and then this changes. This changes to Im sine omega et plus how am I going to say that? All right, no, let's not do that. Okay, now looking at this here, we have two parts. This bit here is only a function of n. Similarly, similarly, this bit here is only a function of n. And when we substitute this part in, we're just going to get the cosine omega et, right? So what do these two terms give us? This is a spatial term. This is temporal, spatial, temporal. These are just functions of n. So let's just look at what those would give us. So note that. So if we have sine 2 pi n over 3, n, let me put n over here, n 1, 3, 5, 7, 9, 11, 1 minus cosine 2 pi n over 3, like that. So when n is 1, this gives us square root of 3 over 2. When n is 3, this is going to give us 0. When n is 5, it's going to give us a minus square root of 3 over 2. N is 7, it's going to give us square root of 3 over 2. And then when n is 9, it's going to give us 0 again. And then 11 minus square root of 3 over 2. Okay? And then on this one, when n is 1, it's going to give us 3 over 2. When n is 0, when n is 3, it's going to give us 1 minus 1 is 0. So that's what I said before. No third harmonic. When there's neutral. When n is 5, we have 3 over 2. N is 7, 3 over 2. N is 9, back to 0, and then 3 over 2. So we can see that this term always is going to give us a positive 3 over 2. That's the first term here. The second term, that's going to alternate between negative and positive, and then there's going to be some zeros on the third and the ninth harmonic, similarly on here. Okay, so with that understanding, we can see that this is these terms can be used to replace the index terms. So let's do that. So I'm going to group them into two parts. So we have that maybe I might run out of space, so let me do it over here. So we'll have MMF is equal to 4 NW. Now I've taken out the IM, and so if we look at 1, 7, those, and then the next one 13, those ones will be the same values. Okay, so we could write n is 1, 7th, 13th, and so on. We're going to have kn, and the first term is 3 over 2, so we'll have a 3 over 2 here, sine np theta over 2 times sine omega et. And then the second one, we have the square root of 3 over 2. We also have a square root of 3 here that would have been put in, so that will give us 3 over 2 as well. So we'll have plus 3 over 2. Again, that's because there's a square root of 3 here and the square root of 3. So we get 3 times cosine np theta over 2 times cosine omega et. Like that. Plus, second term. Now, if we look at, so there's no 3. Now this, the fifth is a negative. The 11th is negative. The 17th would also be negative. So we'll have the 4 NWIM over pi times, and then here's n equals 5, 11, 17, and so on. And that's Kn times 3 over 2 sine np theta over 2 sine omega et. Now we have a minus here because of the minus signs here. Remember, this is the first part, so that doesn't change for either of it, for either part here. But we have a minus, so we need to change the sign on this term. Cosine np theta over 2 times cosine omega et. Like that. And I'll call that equation 13. Okay? So now we're really looking at what's existing. We can further take one step further on this. So using the trig identity, cosine A times cosine B plus minus sine A sine B is equal to cosine A minus plus B. So if we use this, we can then note that, so 13, actually I'll write it over here. 13 now becomes MMF so they all have 3 over 2. So let's take that out. And 4 NWIM over pi. And now, if we compare, here we've got the cosine and sines, so we can replace it with just there's the plus here, so we can replace it with the, so if it's a plus here, it becomes a minus within, so we can reduce this down to a summation here, n equals 1, 7, 13, kn cosine n p theta over 2 minus omega e t minus, and then summation 5, 11, 17 kn cosine n p theta over 2 plus omega et, like that. So we're not going to have a third, but we're going to have a fifth, a seventh, 11th, and so on. 15 is also not going to be present in this case. And remember, Kn would account for the, it would have the distribution factor, the pitch factor, all of these factors in it. We can look at the direction of motion. So recall from waves that if we take the derivative of this term in here and set it equal to 0, that will give you the position change of the wave. So take the derivative with respect to time. So we have and assume it's not changing in position, so you stay at the top point of the wave. So here we would have np d theta dt minus omega e. And so if it's staying in the same position, then the angular velocity or spatial traveling, so this is the traveling air gap field around the rotor, would be given by this here. And so this is a minus, this is a plus, so we could have here plus minus. So what this tells us is that these waves are traveling in the opposite direction to the fundamental. So this is of concern. If you have a large fifth harmonic, for example, you could get a lot of torque ripple. Okay, does that make sense?